Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Science Thursday, we're going to talk about my first ever discrete component lab bench power supply. Now, this puppy is basically made via, I used to have an audio amp and there was no use for it because we did not have any speakers. So I just scavenged parts from it and the chassis from it, and it does work. This puppy does work as intended, as in the voltage control, the current control, everything I wanted. So what we are talking about here is very simple, so to say. So originally, because you have to understand, it's one of the most what you call basic thing that you should build. Let that be very clear. If you're looking into electronics, it's one of those things that you must do. Again, does not need to be master in it, but at least you should do it. Trust me, it's one of those things. Like you open any electronics project book, the first thing would be a power supply. So main essence is, because again I do not know enough about electronics, so I wanted to replicate this. This is from Sign Lab. Now it's a coming from another YouTuber. He knows too much. That's the problem with the schematics. It's way too complex. It's using LM317, which is a normal IC. However, it does come with a consequence that it cannot go to 0 volt on its own. So you have to provide negative volt in order to force it to 0 volt. Now 0 volt is compulsory for a lab bench power supply in order to achieve what we call current control, because there is no such thing as current control. So whenever a short circuit is detected by a power supply, all it does is pulls down the voltage to 0. But again, if you cannot pull down the voltage to 0, you're stuck. So that's why in this design there is a negative voltage rail with negative charge pump with LM337 that is generating minus 125 volt. I did try to build this and I lost my brain. I could not get it to work, and after trying too much, it was like, this is too complex. And heck, for some reason this guy has LM334Z. This is a constant current IC. It's bonkersly expensive, not something that you can just like ta-da. So yeah, that was and again surprisingly expensive in India. Either he has a lot of stock of it, or for some reason it's has some weird tax into it. It was way too expensive, and he was using basically a Zener diode for voltage reference, which is odd. So after going through all of this, I was like, yeah, this is not going to work for me. So I have to learn how to make a power supply. So before you get into any sort of project, you have to constrain what the hell you want. So first thing, a lot of parts were constrained by the audio amp, as in like this is the audio amp. The transformer is 18018. So again, whenever you are getting a transformer that has center tap, do not use full bridge rectifier. You have to understand they are designed so they can be half wave rectified and you still get full benefit. And what's the benefit? Benefit is you only lose 1 volt under high load scenario. If you use full bridge rectifier, you lose 2 volt, because current is going through a diode, returning through a diode. In half bridge, it comes through a diode, goes through direct 0 point. That's why transformers are designed with center tap in the first place. That's by design. So utilize it, don't waste it. Again, you do have a penalty that like for example this 0 transformer, I can take that and make it into 36 if I use full bridge, but again they're not designed for that and current would be too low. So that's one of those things. So it has to be simple, and my target was to achieve 0 volt, which again necessary. Second, negative voltage rail. There should not be any negative voltage rail. So I selected the parts. Now thankfully there is a replacement for Zener diodes. As you can see, these puppy, which we call programmable voltage reference, or like programmable Zener also called by TL431. These puppies are cheap. They are super complex, but they're cheap. Why they're cheap? They are used everywhere. And I mean everywhere. Most power supply have this. So these are super cheap and bulk buy. So I bought this, and they are also very temperature resistant. For example, a Zener diode will change a lot based on temperature. These things are far more resilient to that. And again, that's why, like if you look at laptop power brick, there is a good chance it has this or something like this. So this was that. And then for potentiometer, I selected the port, 10-ton port. Is it necessary? Sort of, yes, because again, the pot that are available nowadays, they are way too Chinesium, and good luck, they are very dangerous, because again, the build quality is so random that you might get something that works fine, or you might get some that randomly jolts and goes to 0 volt or goes to full volt, which is very destructive. So, and again, you will not get enough control. You could try chaining 2 of them to have, like, 4 basically coarse and fine adjustment, but so just get a 10-ton pot. Yes, they are expensive, like almost $2, or in case of India, I got these for like 125 rupees. but again decent enough. And in terms of op amp, thankfully op amps are a base of everything electronic, so I bought a kit that had like this sort of 5 things, LM358, and I only fried one of them, so surprisingly good with that. LM358 is like default, and you're like, it's not great, it's slow. Does not matter. It's my first project that I was designing with it, so my whole intent was design something that does not have negative voltage rate, design something that any Tom, Dick and Harry can build, including me, and it should be able to achieve 0 volt. Now, did I achieve 0 volt? Sort of. I achieved 0.003. That's the lowest I could get. If I use modern op amp, I could get it down to with a compensation pin to almost 0, but I'm fine with that because most multimeter does not show it unless you set it to microvolt. So I'm very happy with that. And transformer was already selected, and thankfully 18018 transformer is really good for 12 volt system, because 12 volt systems, whenever you, let's say you're looking into car headlights or cigarette charger or anything, even lead acid battery, they not charge at 12 volt, they charge at 14 volt. So having 0 to 15 volt range allows you to test those things also. So that was a very deliberate system. Now we're going to go into schematics, and I'm going to explain every part of the schematics. And after that schematics, I'm going to open the power supply, and you guys can have the look into the horrors of it. But it does work. And again, I want to show that horror for one very simple reason, so you can understand that, like, whenever you're watching like some pro YouTubers, like, making things that looks like even better than what you can buy, is generally after a lot of painful realization, lot of practice. And again, sometimes that could be demotivating. So I'm showing this just to, give you a sort of freedom, where it's like, hey, it will look like poo poo. After a while, you will like, oh, now I know how to make it, how it looks perfect and all that. So let's move into schematics. So let's dive deep into the schematics. So this is just a comparison diagram from Sine Lab. Now again, either he has access to very cheap LM334Z. This puppy is very expensive in India for some reason, and this is very complicated because you can say he's using LM317. That limits him, because without having a negative voltage from here, this puppy will not go to 0 volt. However, this schematics diagram allowed me to actually understand how the current control works. That's the best part about this. So you can see there is a shunt resistor. By the way, there is no such thing as quote unquote current control. All there is voltage control. So whenever your current exceeds, what are you doing? You are just dropping the voltage. Ohm's law. So you have a shunt resistor here, 100 milliohm, and in this puppy you get a voltage drop based on the current. So let's say you get a 0.1 volt drop when you are drawing 1 amp of current. So what you do is this shunt resistor, but be mindful, this has to be power resistor, something like this puppy. Now again, this is overkill, 25 watts, but generally you will get 5 watts and 100 milliohms. You could use a bigger resistor and bypass the what we call gain stage, not recommended. Generally you want to reduce waste heat, so it is unwise to have that. So you have 100 milliohm. Now he amplifies it by 10x. That's why your 0.1 volt will become 1 volt. So if this op amp is giving you 1 volt, that means 1 amp of current is being drawn. So you have like 100k, 100k, 10k, 10k. That is the 10x multiplication. One important thing, make sure the higher voltage side goes to the positive, negative goes to the system. Yes, I know inverting and non-inverting, but it's very confusing. So I just say positive and negative. I wasted like almost few days just figuring out this mistake. Okay, this gives you amplified signal. You can sense it here, TEP sense here. What after that? Well, you have to use comparator, as in whether this is on higher or the user input. How the heck you get user input? In this design, this is the user input, and this comparator pulls down this. That's it. So this was a really good helpful thing for me to understand, because this is the best I have seen in terms of current control. Now, this is what I have built. Now be mindful, any pro can build better than this. This is bare minimum. This is just to get you started, not final system. So we start with basically your input. Now input in this design is DC input. I already had a separate bridge rectifier board, as in like the board has bridge rectifier and capacitor and all that. Be mindful, do not use basically full bridge rectifier if your transformer is 18018 or 15015. Don't do that, because again, they are designed specifically so you can use half bridge rectification and save voltage. Because if I sent basically 10 volt, 10 0 10, if in a full bridge rectifier there are two what you can say basically current has to flow through one diode and flow back through another diode. That creates in this negative design. So basically 1 and return is here. That means you have 0.7 loss here and 0.7 loss here. That's why people design does not use transformer like this. They are always center tapped for this exact return. So you can only have 0.7 loss, or at load 1 volt loss. If you have like full, you get 2 volt loss. And again, it's a linear power supply. Voltage loss is the key. You don't want your rectifier to lose most of the voltage. So that's why please use half rectification, or like butterfly phase rectification. So assuming you have DC, you can even feed it with a laptop power charger. So once you have DC, that becomes the VCC. So what is happening? The voltage is going. This is Darlington pair transistor. This transistor is acting like a resistor. What does that mean? That simply means it's going to burn off. It's a resistor that is controlled. And then you get your V out. That's what's happening. If voltage comes in, this dynamic resistor adjusts itself, so you get the right V out. Cool, awesome. So how do we get that? Well, you start with basically VCC requires a reference. So I'm using TL431, this puppy. I would recommend using this. They are very high basically they are foundational on almost all SMPS, so they are very cheap and you can buy bulk of them for like nothing almost. Even in India, they are very cheap. And again, they have very good temperature stability compared to any Zener diode. This will bitch slap it. So use this. I have done divided by 2:1 because the Zener is designed for 2.1. And again, based on a resistor divider, you can control the voltage. In my design, I'm focusing on 5 volt. You can change it higher or lower, but I would recommend stay at 5 volt. So this becomes my VREF. VREF is 5 volt. This resistor divider, tada, 5 volt. Okay, what after that? After you get the 5 volt, it goes to a user input, which is this puppy. So one of the leg of the potentiometer would be ground, another leg would be 5 volt. Now, based on this, the wiper will give you something between basically 0 volt and 5 volt. That's what V pot is, and that's the same thing current pot is. So you get your signal. Now this signal goes into basically LM358, the op amp. This goes into the positive side of it, first op amp positive side, and this output controls the transistor. But here's the deal, it needs feedback. So how the heck you get feedback? You get feedback from this section, what we call a resistor divider, voltage divider, so to say. And this is 10K by 5K because again, my user signal is only 5 volt, but I need to control up to 15 volts. So I need this divider to handle it. So all this op amp is doing is comparing this point versus this point, which is up or down. And based on that, it either turns it on or off in order to give you the right voltage. That's the voltage control. That's the primary control loop. And after that, you voltage goes through shunt resistor, so 100 milliohm shunt resistor. Because I wanted more what you call current range. Like target was 3 amps. This 100 milliohm goes by 3K to 100K, 3K to 100K, tada, 30x. And then it goes into second op amp, second LM358. So this will give me an output signal here based on the voltage. Basically, if I'm reading 3 volt or like basically I wanted to scale it up to 5 volts, so I'll get something weird, basically 1.6. You can use your multimeter to test it out how much you're getting. And once I have that, I'm using the second op amp in this. Be mindful, the LM358 has 2 op amp. So I'm using one op amp as current amplifier, another as a current basically comparator. So comparator reads the input from user, as in user potentiometer, goes tada, V in, and then op amp compares it. It's like it will turn this puppy off. It will not do anything as long as this user input is above. Like user has set for 1 amp, the current draw is below this, it does not care. The moment current goes like short circuit or over current scenario, this turns on this 2 and 2. Now why turn this on? So it can pull down the V signal, as in the voltage signal, it turns it down. It turns down after, let that be very clear, after the user input. So user could have set 3 volts. This will allow it to shut down that to 0 volt. Once this becomes 0, op amp drives this until this becomes 0 and voila, no more voltage. That's how it works. And you have to have some capacitor because LM358 is not the greatest op amps, and op amps oscillate. So this capacitor is like a shunt path for high voltage signals, high frequency signal, because again, capacitor is a conductor for high frequency. It's a isolator for DC, but for basically high frequency, signal will bounce back between this and the output. So it will basically, the op-amp circuitry that is inside will not see it anymore. So that's why you use 1 nanofarad or 10 nanofarad depending on your design. Generally 1 nanofarad is fine enough, and that's why this capacitor is also there. These are soaking up the oscillations that could happen at the edge cases. And be mindful, never drive a transistor directly from the op-amp. I did fry one of these sweet puppy LM358. So generally make sure you have a 2 kilo ohm resistor to limit the maximum current that can go into 2 and 2. And again, I made this Darlington pair in my design, but it's not necessary. You can just buy a Darlington that has basically these two signal transistor, current transistor, resistor, discharge resistors, and then diode. All of these are available as one package, Darlington pair. I have ordered them. They should come by tomorrow or a day after that, and that will be for my next design, where instead of making this mess, I'll just have multiple of those. So this is my very minimum, bare minimum basic system. And again, it's a very good starting point. Then you can add basically shutdown system to it, flowback system. Be mindful, make sure you have this diode. Again, look into almost all designs that are linear power supply. They will always have a diode. Look into LM317 use case datasheet. It will also have a diode. You need diode in order to, like, what if somebody puts a capacitor, boing, it goes there. So you will get current control from this stage. You will get voltage control from this, and user can do that everything. Now be mindful, it does not go to pure zero. That's op-amp limitation. It only goes to 0.003 in my design. But be mindful, unless you set your multimeter, like you set your multimeter to millivolt, you will not see the signal that well. And again, the onboard digital meter I have, that goes to 0. So I'm happy with that. You could, I was thinking about what if I use this measurement from here and then drive this puppy. It was too much. I'm happy with 0.33, and current also becomes very low. It's like microamps, milliamps. So you are only drawing microwatts of power at worst case scenario, which is, it will not fry any fuse or even any microcontroller. So I'm happy with that. One important thing, this is very digitizable. For example, if you want to make this into digital system, it's gonna be one part would be easy, other part would be hard. Like for example, this pot will be, how the heck you digitize a pot? It's not that easy. This you can, but voltage you can't. In my design, that's why both are being controlled by op amps. Meaning, for this voltage input, you need ADAC, basically. DAC, digital to analog converter. Your op-amp, basically your microcontroller can feed signal here, and that will become the current and voltage signal. Okay, that tells what I want, but what about the feedback? Well, for feedback, again, let that be clear, this system will work if only you have this, but you want, generally, if you are going to microcontroller, you want to read back. So for read back, you will have analog to digital converter here that reads back basically signal of voltage from here, and then you have another from this gain stage. This can be read back, and benefit of this is all system is designed from 0 to 5 volt. Your normal average microcontroller should be able to handle that. But be mindful, please, if you want to do this and you want good granularity of voltage control, buy something like that has 4096 levels, 10-bit, 12-bit DAC, those sort of things. But again, this is the design, and I'm gonna open the box and I'm gonna scare you all because this looks like hideous inside. And again, that's how your Mark 1 will look like. Once you have 10 to 12 years of experience, lot of projects, it will look beautiful, but Mark 1 will not look like that. So I just want to show that so you do not get discouraged. Ta-da! Let's turn it on. This is voltage, this is current, this is constant voltage, this is constant current. Output is 0, this is the switch. Turn on the switch, ta-da! The voltage goes to 15. This is 10-ton pot, I can keep reducing. As you can see, the voltage is going down here also. Keep dropping the voltage. This is very slow, that's why I'm using this. Refresh rate of this monitor is a bit slow. But ta-da! 0, and it is almost like 0.003, so it's a very decent 0. And again, I can turn on some LEDs for testing purposes. Let's see. Let's just see whether it works or not. I think I have to increase the voltage. Ta-da. Ta-da. I'm pretty sure it's capturing camera. So negative, positive. Ta-da. Current was also showing. Oh, this is basically 9 voltage. This is a 12 volt LED. It should start at 9 volt. So let's see. Let's increase the voltage to. It's a 12 volt cob, so that's why I'm expecting that. Oh, damn. Damn, this puppy is bright. This puppy is bright. So, did it get hot? No? Damn. So that's the whole point of having voltage and current control. And again, I can set a current too low, current control, that it will drop the voltage automatically because, ta-da, that's the whole point. So current control also works. If I push it too much, like for example, and if I short it, let's see what happens. Ta-da. Oh, this is one side effect of having basically 10 turn per hour. It does take some amount of time. So let's see how much current I get. Let's reduce it a bit. This time I'm only getting, that's the whole point. Current control is working. Ta-da. So this is how the system works. All thing is well. Again, lot of more love needs to be put into this to make it like a pro grade situation, but so far so good, and I'm happy with it. Again, now let me show you the inside of it. That's it. Again, this is how your early prototypes will look like. Of course, I'm gonna redo this with better design and thought process, but so far I'm happy with it. It does work, and I do utilize this, so to say, plug. It's locking plug. You cannot basically pull it out unless you pull this. So that's on the lower end, and that also has a fuse. Oh, and because I have basically two transistor, you can see I have basically resistors, basically two what you call ballast resistor, in order to balance these two things, balance these two. Otherwise they will basically, one of them might burn up if that is not there. So again, this is how my first ever prototype looks. Of course, wish me luck so I can make a Mark II that is a bit better.